I want you to picture a scenario. It's the end of the month. You've been working your tail off at your job for weeks. You've clocked the hours, you've done the heavy lifting, you've sat through those endless meetings that could have been emails, but you haven't actually been paid. Not in cash.
That would be a significant problem for most people.
A huge problem. Instead of a direct deposit hitting your bank account, your boss has just been handing you these little slips of paper, promissory notes, vouchers, good for one payment later.
Right.
You've got a stack of them on your desk, but you can't go to Starbucks and buy a latte with a sticky note that says, I owe you.
I love this analogy.
Mm-hmm.
Because if you've been following our deep dives on metabolism, especially the last few, that is exactly where we are right now.
We've done the work, right? We went through glycolysis, breaking down the sugar molecule.
Yeah.
We spun the wheel of the citric acid cycle. We stripped all those carbons off. We did the chemical heavy lifting.
And what did we get for it? I mean, we got a tiny bit of ATP, the actual cash of the cell, but mostly we got checks.
NADH and FADH2.
Exactly. These are high-value checks, don't get me wrong. They represent a massive amount of potential energy. But the cell can't spend NADH to contract a muscle or pump an ion or fire a neuron.
The rent is due, the landlord is knocking.
And we are sitting on a pile of paper vouchers.
So today we are finally going to the bank. We are doing the final accounting. This is our deep dive on oxidative phosphorylation.
And I have to say, even though the name sounds so dry, oxidative phosphorylation, this is, and I'm not using hyperbole here, this is the most sophisticated piece of machinery in the known universe.
That's a big claim. The universe is a pretty big place.
It's the only claim that really fits. We're going to be looking at a process that takes place on a membrane that's only, 70 angstroms thick?
Wow.
A membrane that is currently, right now as you're listening, acting as the barrier between you being alive and you being dead.
High stakes.
The absolute highest. We're drawing from Leninger's Principles of Biochemistry to understand the mechanics. And when I say mechanics, I mean literal rotary motors and piston pumps inside your body.
It's incredible.
And we're using Harper's Illustrated Biochemistry to look at the darker side, the clinical reality, the poisons, the genetic failures. Because when this bank closes, the lights go out permanently.
So the mission is simple. Follow the money. We take the checks NADH and FADH2, we walk them into the bank, which is the mitochondrion, and we see exactly how they get cashed.
Yes. And as always, we should probably remind everyone, this is a synthesis. We're interpreting these massive textbooks to help you build a mental map.
Right. You have to read the books.
You have to read the books. Leininger gives you the engineering diagrams. Harper gives you the medical chart. We're just the tour guides connecting the dots.
So let's connect that first dot. We're talking about electron transport. We've harvested electrons from our food, but why are they moving? Why don't they just stay put?
It's not magic and it's not random. It's physics. Specifically, it's about a concept called standard reduction potential.
Leininger throws a symbol at us here. E prime 0.
Right. And you could just think of this as electron pressure. Every molecule in the universe has a specific relationship with electrons. Some molecules are generous. They want to give them away. Some are greedy. They really want to steal them.
And this is oxidation and reduction.
That's it. Harper defines it really simply. Oxidation is losing electrons. Reduction is gaining electrons. But Leininger gives us the voltage numbers, and that's what tells us the force of that desire. It quantifies the greed.
Okay, so let's look at our starting player, NADH. This is the big check we're holding.
NADH is holding a pair of high-energy electrons it picked up from, say, glucose. Its standard reduction potential is negative 0.32 volts.
Negative means what? It wants to sell.
Negative means it is under high pressure to release.
Yeah.
It really, really wants to get rid of those electrons. It's holding a hot potato. It's looking for anyone to take them.
And at the other end of this whole chain, who's the ultimate buyer?
Oxygen. Oxygen is the ultimate electron-hungry beast in biology. Its potential is positive 0.82 volts.
So we have a gap from negative 0.32 all the way up to positive 0.82.
That's a total span of 1.14 volts.
Okay, but help me out here. 1.14 volts. A standard AA battery is what, 1.5 volts? That doesn't sound like a lot of power to run a human being. It barely runs my remote control.
That's the trap. That's where our intuition just completely fails us. 1.14 volts doesn't sound like much on the scale of a flashlight.
Right.
But you have to consider the distance. We are talking about a voltage drop occurring across a tiny molecular wire over distances measured in nanometers. When you calculate the field strength, the volts per meter, it is absolutely massive. It is like a thunderstorm inside the protein.
So the electron really wants to get from NADH to oxygen,
desperately,
Yeah.
energetically. It's like a boulder sitting at the very top of a massive cliff, and oxygen is the valley floor. Gravity, or in this case, redox potential, dictates that the boulder must fall.
But we don't just let it drop, do we? Because if I drop a boulder off a cliff...
It smashes into the ground, it creates heat, sound, chaos. If we let electrons jump straight from NADH to oxygen, you wouldn't get ATP. You'd get a combustion reaction. You would essentially create a little explosion of heat that would incinerate the cell.
So biology has a problem to solve. It has this massive potential energy, but it needs to harness it without burning the house down.
Exactly. We need to control the fall. We need to build a series of gentle steps. We need a bucket brigade.
A bucket brigade, I like that.
Imagine the electrons are water in a bucket at the top of a hill. Instead of dumping it all at once, we hand it to a person one step down. You hand it to a person one step down from them. And at each step, we use the energy of that handoff to do a little bit of work.
And that is the respiratory chain.
Correct. It's a series of carriers, each one arranged by increasing affinity for electrons. We pass them from NADH to something that wants them a little more, to something that wants them even more, until they finally, gently, land on oxygen to create water.
And that water creation, that is literally why we breathe.
It is. You don't breathe oxygen just to have it floating around in your blood. You breathe it to act as the final trash can for spent electrons. If you don't have oxygen there to catch them at the end, the whole line backs up.
The bucket brigade stops.
The whole thing grinds to a halt, and you die within minutes.
Okay, so we have the logic, we have the why. Now let's get into the where and the how. We're going into the inner mitochondrial membrane, the IMM.
The IMM. This is the barrier. And the key feature you have to just burn into your brain here is impermeability. Lehninger really stresses this. This membrane is a vault. It generally does not let ions pass through, especially protons, hydrogen ions, H++6.
And why is that impermeability so important?
Because we are about to build a battery.
Okay.
And to build a battery, you need to separate charge. You have to keep the positive on one side and the negative on the other. If the membrane leaked, the battery would just short out instantly.
Got it. Sealed vault. Now, embedded in this vault are these massive protein complexes. We call them complex 1, 3, and 4. Let's walk through them. First up, complex 1.
Also known as NAGHQ oxidoreductase. And complex is definitely the right word. This thing is an absolute beast. Lehninger describes it as L-shaped.
Like a boot, or an L on its side.
Exactly, like a boot. One leg of the boot is embedded deep in the membrane, and the other leg sticks out into the matrix. That's the very inside of the mitochondrion.
So our NADH comes swimming up to that leg that's sticking out.
It docks, and it hands off its 2 high-energy electrons. And this starts a sequence that feels more like, steampunk engineering than biology. The electrons hop onto a molecule called FMN flavin mononucleotide, and then they start jumping through a series of iron-sulfur centers.
Iron-sulfur centers. I always picture these as little cages, like a wire mesh.
They are. They're literally molecular wires, iron atoms caged in sulfur that allow electrons to hop through the protein. But here is the real insight, the thing that changes how you see this. As those electrons move through the wire, they change the electrical charge of the protein.
Okay, so the wire gets hot, initially, electrically speaking.
In a way, yes. And that charge change triggers a shape change. A conformational wave ripples through the entire L-shaped complex. Lehninger describes this long alpha helix, a rod of protein that runs the length of the membrane arm.
A piston rod.
It's literally a piston rod. The electron movement causes this rod to slam sideways. And that mechanical force, that physical movement, opens up channels and forces 4 protons from the matrix, the N side, all the way across to the inner membrane space, the P side.
That's just incredible. So it's not just a chemical reaction, it's a tiny combustion engine converting a spark into physical movement.
It is a proton pump powered by electron torque. It's taking protons from where they want to be on the negative side and forcibly pushing them where they don't want to be on the positive side. That is work. That's storing energy.
But because it's a machine with moving parts, it can be jammed. This is where Harper comes in with the toxicology.
Right. Because this system is so vital, it's a prime target for poisons. And Harper specifically mentions barbiturates here, drugs like amobarbital.
Which are painkillers, sedatives. How can they stop a machine this big?
Well, they don't have to destroy it. They just have to block the exit. Barbiturates bind right at the spot where the electrons try to leave that iron-sulfur wire to get to the next carrier, which is called ubiquinone.
So the electrons just pile up inside complex I. They have nowhere to go.
They hit a wall. And think about the physics of that. If the electrons can't move, the charge doesn't shift. If the charge doesn't shift, the piston can't move.
And if the piston can't move?
No protons get pumped. The battery stops charging.
And the lights go out.
The brain is the first to feel it. That's why these drugs cause sedation and, at high doses, coma and death. You are quite literally powering down the engines of consciousness.
That's terrifying. Okay, so let's assume we haven't been poisoned by barbiturates.
Yeah.
The electrons leave complex I and jump onto a carrier, ubiquinone.
Or coenzyme Q. We usually just call it Q. Yeah. This is a fascinating little molecule because it's not a protein. It's a lipid-soluble benzoquinone, which basically means it lives inside the membrane bilayer.
It's hiding in the greasy part of the wall.
Essentially, it's like a little submarine that swims through the fatty interior of the membrane, varying electrons from complex I over to complex 3.
Wait, you skipped complex 2. We went from I to 3. What happened to 2?
Yes, complex 2, the underdog. Complex 2 is actually an enzyme we've met before. It's from the citric acid cycle. It's succinate dehydrogenase.
Oh, right. The one that makes FADH2.
Correct. This is the side door to the respiratory chain. So complex 1 is the grand entrance for electrons from NADH. But complex 2 is a different entrance for electrons from succinate. Via FADH2, it passes them to Q, just like complex I does.
But there's a catch, isn't there? I seem to remember from the textbook that complex 2 is physically smaller, less complex.
It is, and this is the crucial distinction. Complex 2 does not pump protons.
So it's lazy.
It's not lazy, it just doesn't have the energetic cash flow to do it. The redox potential of FADH2 is much closer to zero. It's not negative enough to generate the kind of force required to pump a proton. So FADH2 contributes its electrons to the chain, but it contributes nothing to the gradient at this step.
And this explains the accounting difference, right? Why NADH is worth more ATP than FADH2.
Exactly. This is the reason. NADH enters at the top of the water slide at complex 1 and gets to hit all 3 pumps. FADH2 gets on halfway down at complex 2, and it misses that first pump. It just generates less power.
Okay, so Q, our little submarine, collects electrons from both complex 1 and complex 2. It swims through the grease over to complex 3. What happens there?
Complex 3 is called Q-cytochrome C oxidoreductase, and this is where the engineering gets really, really tricky. Leniger spends pages on this because nature had to solve a fundamental mismatch in the system.
What's the mismatch?
It's a plumbing problem. The carrier coming in, that's ubiquinone, or Q, holding 2 electrons. It's 2 electron to carrier. But the carrier going out, which is cytochrome C, is a tiny protein that can only hold 1 electron at a time.
So you have a 2-gallon bucket and you're trying to pour it into a 1-gallon cup.
Without spilling a single drop, and if you spill an electron here, you create a free radical, which is incredibly toxic to the cell. So the cell evolved something truly elegant called the Q cycle.
A Q cycle. Okay, how does this work? Give me the simplified version.
Think of it like a specialized airlock, or maybe a turnstile. Q comes in with its 2 electrons. It docks. The first electron goes straight to cytochrome C, the outgoing carrier. That's the easy part.
Okay, 1 down. What about the second one?
The second electron takes a detour. It gets recycled. It loops back around inside complex 3 and is temporarily stored on a waiting Q molecule.
So it's put in a holding pattern.
Exactly. Then a second fully loaded Q comes in from the membrane. It sends its first electron out to a new cytochrome C, and its second electron joins the one that's been waiting in the holding pattern. That regenerates a fully loaded Q molecule inside the complex.
That is dizzying. It's like a traffic roundabout for electrons.
It's amazingly efficient. By splitting the stream and recycling that second electron, complex 3 manages to pump a total of 4 protons out. It squeezes every last ounce of energy out of that transfer.
Maximizing the gradient seems to be the mantra of the mitochondria.
Absolutely. Every single electron movement must result in a proton pumped. No wasted motion.
So cytochrome C now has an electron. Where does it go?
Cytochrome C is another mobile carrier, but unlike Q, it's a protein that just kind of skims along the surface of the membrane. It's like a little ferry boat, and it takes that electron to the end of the line, to complex 4.
Cytochrome C oxidase, the grand finale.
This is it. This is the big one. Complex 4E takes the electrons and finally hands them off to oxygen. But this is probably the most dangerous handoff in the entire body.
Why? I mean, we breathe oxygen. It seems pretty safe to us.
Oxygen is safe when it has 4 electrons, because that turns it into 2 molecules of harmless water. But if you give oxygen just 1 electron, you get superoxide. If you give it 2, you get peroxide. These are what we call incomplete reduction products.
The chemical saw blades.
They will tear apart lipids, proteins, DNA, anything they touch. So complex 4D has to be perfect. It can't just dribble electrons onto oxygen. It has to hold the oxygen molecule in a vice grip.
Leninger details the structure here. There are these heme A3 and copper B centers.
Right. Think of it as a molecular clamp. It grabs an oxygen molecule, O2, and holds it tight between an iron atom and a copper atom. It just waits. It waits until it has collected all 4 electrons from 4 different cytochrome-shaped molecules, and only then does it dump them all into the oxygen at once, adds 4 protons from the matrix, and bam! It releases 2 perfectly formed, safe water molecules.
Clean, no leaks.
Ideally, yes. And while it's doing all of this, it pumps 2 more protons across the membrane.
So let's just recap the score. For one NADH, complex I pumps 4, complex 3 pumps 4, and complex 4 pumps 2. That's 10 protons pumped out for every single NADH molecule.
Precisely. We have built a massive gradient. The intermembrane space is now full of protons. It's acidic. It's positively charged. The matrix is alkaline and negatively charged. We have created a biological capacitor, a charged battery.
But before we use that capacitor, we have to talk about what stops complex 4, because Harper mentions some very, very famous poisons here, the classics of every murder mystery novel.
Cyanide, carbon monoxide, hydrogen sulfide.
How do they work? Why are they so deadly so fast?
They work by mimicking oxygen. They bind with an extremely high affinity to that heme A3 center in complex 4E, that clamp we just talked about.
So they steal oxygen's seat.
They steal the seat and they lock the door behind them. Cyanide binds to the iron atom, and it just refuses to let go. It essentially pours concrete over the final spillway of the dam.
And if the electrons can't leave complex 4...
Then they can't leave complex SIR. Then they can't leave Q. Then they can't leave complex 1. The entire bucket brigade stops. The whole chain backs up instantly.
And the proton pumping
Stops immediately. The gradient collapses. ATP production hits absolute zero. You lose consciousness in seconds because your brain has no reserve power. It's terrifying how purely mechanical it is. It's like jamming a single gear in a clock. The whole thing just stops.
It really emphasizes that life on a razor's edge theme from the beginning. We were all just a few milligrams of cyanide away from a total system shutdown.
It is the fragility that comes with incredible efficiency.
So assuming we haven't been poisoned, we've successfully built this gradient, we have protons literally screaming to get back inside the matrix. And this brings us to a major turning point in the history of biology, because for a long time, nobody knew what this gradient was for.
This is the story of Peter Mitchell and the chemiosmotic theory.
Set the scene for us. It's the 1950s.
Okay, so in the 1950s, biochemists knew that electron transport happened, and they knew ATP was made. But they assumed it worked just like glycolysis, what we call substrate-level phosphorylation.
Meaning they thought there was a direct chemical reaction where a phosphate gets passed from one molecule directly to another.
Right. They were hunting for a high-energy intermediate, a phantom molecule. They literally called it X-P in the literature. They thought the electron chain made the supercharged chemical, and then that chemical was used to make ATP.
And people spent their entire careers looking for this molecule?
Decades. Entire labs, famous biochemists, they were all hunting for this X-P, and they couldn't find it because it didn't exist.
And then Peter Mitchell comes along in 1961 and says, what?
He says, stop looking for a molecule. Look at the membrane. He proposed that the energy isn't stored in a thing, but in a state, in the separation of ions, what he called the proton motive force.
That must have sounded completely insane at the time. The energy is in the empty space between the walls.
It was incredibly controversial.
Yeah.
I mean, he was practically laughed out of conferences. But he was right. Leninger breaks this force into its 2 parts. There's the chemical potential, the delta pH, that's the acid on the outside versus the alkaline on the inside.
Okay.
And then there's the electrical potential, the delta psi, that's the positive charge on the outside versus the negative charge on the inside.
So the membrane is acting like a dam. The protons are the water being held back by the dam. And the electron transport chain, all those complexes, they're just the pumps that are filling the reservoir.
Exactly. And the proof of this theory was that if you poke a hole in the membrane, if you destroy the gradient Thabit, the gradient electron transport continues, but ATP synthesis stops completely. They are coupled only by the integrity of that gradient.
Which finally leads us to the turbine, the machine that actually cashes the checks. ATP synthase, complex V.
My favorite protein. It's a masterpiece.
Leninger's description of this is just wild. It's not just an enzyme, it's a motor.
It is a rotary motor, a true nanomachine. It has 2 main parts. There's the FO part and the F1 part.
The FO is the part embedded in the membrane.
Yes. The O actually stands for oligomycin sensitive, which is an inhibitor we'll get to. But you should think of FO as the water wheel. It has a ring of subunits, the C ring, and when protons flow through this channel from the outside in, The ring spins.
Literally spins like 360 degrees, around and around.
Literally spins at thousands of RPM. And attached to this spinning ring is a central shaft, the gamma subunit. This shaft sticks out from the membrane right into the middle of the F1 headpiece.
And the F1 head is where the ATP is actually made.
Right. Now, the F1 head is stationary. It's held in place by another arm. But inside it, that gamma shaft is spinning like a crazed drive shaft. And as it spins, it's kicking the subunits of the head.
It's kicking them.
Well, Leninger explains this as the binding change model, which was proposed by Paul Boyer. Imagine the head has three main slots, the beta subunits. As the shaft rotates, it acts like a camshaft. It forces each of those three slots to change its shape.
What are the shapes? What are the states?
3 states. First, the loose state, in this shape, it combined ADP and phosphate. Then the shaft turns and bumps it, forcing it into the tight state. This physically smashes the ADP and phosphate together to form ATP.
And then
Shaft turns again, and it kicks the slot into the open state. And this shape has such a low affinity for ATP that it literally ejects it. It spits it out.
So it's a cycle. Loose, tight, open. Loose, tight, open.
Over and over in each of the 3 slots. And here is the absolutely mind-blowing part that Leninger highlights. The actual chemistry, the snapping together of ADP and phosphate, is energetically easy on the surface of the enzyme. It practically happens by itself because the enzyme holds them in the perfect orientation.
Wait a second. I thought making ATP required huge amounts of energy. That's the whole point of this entire process.
This is the great paradox. The energy from the proton gradient isn't required to form the bond. The energy is required to release the ATP from the enzyme.
No way.
The enzyme loves ATP so much it won't let go. It has an incredibly high affinity for its product.
So the proton gradient, the spinning motor.
The proton gradient provides the mechanical torque to physically pry the ATP off the enzyme so that a new ADP and phosphate can come in and the cycle can continue.
That is just wild. The energy is an ejection seat.
Basically. It's torque-driven product release. Without the spinning, the ATP would just sit there, stuck to the enzyme forever.
So how much bang for our buck do we get? What's the final exchange rate at this bang?
We call it the PO ratio, the number of phosphates added to ADP per atom of oxygen reduced. For NADH, we pump 10 protons. The best estimates are that it takes 4 protons to make and export 1 ATP molecule.
Why 4? I thought you said 3 for the loose, tight, open cycle.
Good catch. It takes 3 to spin the rotor, but it takes 1 more to power the transport protein that brings the phosphate molecule itself into the matrix. So 4 total.
Okay, so 10 protons divided by 4 gives us
2.5. So 1 molecule of NADH is worth about 2.5 ATPs.
And what about our side door entry, FADH2?
Well, it enters a complex 2, so it misses the first pump. It only pumps a total of 6 protons, so 6 divided by 4 is correct. So FADH2 is a cheaper check. It's worth 1.5 ATP.
It's some seriously impressive accounting. But a system this powerful must need some kind of control. You don't want the engine revving at full speed when the car is just parked in the driveway.
Absolutely. This is the concept of respiratory control. And the key regulator, the master switch, is ADP.
Explain that. Why ADP?
Well, think about it. Why do we burn fuel in the first place? It's to turn ADP back into ATP. So if you're just sitting on the couch watching Netflix, you're not using much energy, you have high levels of ATP and very low levels of ADP.
So the raw material for the machine, the ADP, is scarce.
Exactly. Harper calls this state 4 respiration. It's the resting state. If there is no ADP to bind to the ATP synthase, the turbine can't spin. It's like a turnstile that locks if there's no one there to push through it.
And if the turbine can't spin, protons can't flow back in.
Correct. And if protons can't flow back in, the dam fills up. The gradient gets steeper and steeper and steeper until the pumps complex I3 and IV literally can't push against that massive back pressure anymore. So the whole chain stalls. You stop consuming oxygen.
So no work equals no burning. The system ensures we don't waste fuel.
Right. But then you stand up and start sprinting up a hill. You're hydrolyzing ATP like crazy. ADP levels spike. This is what Harper calls state 3. Suddenly, the synthase has plenty of ADP. It starts spinning like crazy. Protons flood back in. The pressure on the dam drops.
Then the pumps go into overdrive.
The pumps start working at maximum capacity again. You start consuming oxygen rapidly.
That is an incredibly tight coupling. The engine revs perfectly in sync with the gas pedal.
Coupling is the key word. Oxidation, which is burning fuel, is coupled to phosphorylation, which is making ATP. They are locked together.
Unless
they aren't.
Unless they aren't. And this brings us to the dangerous idea of uncoupling.
This sounds like a messy breakup.
It's more like sabotage. Imagine you go to that dam we've been talking about and you drill a big hole in it.
Water will just flow through the hole, not through the turbine.
Exactly. Protons flow back into the matrix without ever touching ATP synthase. The gradient collapses.
So what happens to all that energy? I mean, it has to go somewhere. Physics says energy is conserved.
It is released as heat. Pure, useless heat.
Harper mentions a chemical that does this, a famous one, DNP.
2.4 dinitrophenol. DNP, this is a crazy story. In the early 20th century, DNP was used in munitions factories to make explosives.
And the workers in these factories started noticing something odd.
The workers started losing weight rapidly, without even trying. They were sweating all the time, they were always hot, and the pounds were just melting off.
Why? What was the DNP doing?
Because DNP is a proton ferry. It's a chemical that can grab a proton on the outside, in the intermembrane space, carry it across the membrane, and release it on the inside. It effectively drills thousands of tiny holes in the dam.
So the mitochondria are working at full blast, pumping protons out.
And DNP is just bringing them right back in. No ATP is made. So the cell panics. It screams, "We are starving for energy. We have no ATP." So it burns fat, it burns sugar, it burns everything it has to try and restore that gradient.
So people thought, this is a great diet pill.
And it was sold as one. In the 1930s, it was a huge sensation until people started cooking to death.
Literally cooking.
Literally. Fatal hyperthermia. Remember, all that wasted energy from burning fuel becomes heat. If you take too much DNP, your body temperature rises uncontrollably. You sweat, you pant, but you can't cool down. There's no off switch. It's a horrific way to die.
So uncoupling can be fatal. But biology's clever. It uses this trick too, right? In a controlled way.
Yes. Controlled uncoupling. Newborn babies and hibernating bears. They have something called brown adipose tissue, or brown fat.
And what makes it brown?
It's absolutely packed with mitochondria. That's what gives it the color. And these specific mitochondria have a natural regulated uncoupling protein called thermogenin, or UCP1.
So babies have a built-in electric blanket.
Exactly. Babies don't shiver well. Shivering is just muscle contraction to make heat. Instead, they use this brown thought to short-circuit the gradient on purpose.
Yeah.
They burn fat, not to make ATP, but to generate heat to keep their vital organs warm. It's a brilliant survival mechanism.
That's amazing. So DNP is a leaky dam. What about oligomycin? You mentioned the O in FO stands for oligomycin sensitive.
Right. Oligomycin is an antibiotic produced by a species of Streptomyces bacteria. And it's toxic to us. It doesn't poke a hole, it does the opposite. It plugs the turbine.
It welds the water wheel shut.
Perfect analogy. It physically blocks the proton channel in FO. So protons can't get back in at all. The gradient gets impossibly steep. The pumps can't work against the back pressure. Respiration stops cold.
So let's make sure we distinguish these two. Uncouplers like DNP speed up respiration but kill ATP synthesis. Inhibitors like oligomycin kill both because the whole system backs up.
Perfectly stated. One is a leak, the other is a plug. Both are fatal.
We've talked about the mechanics, the regulation, the poisons. Now let's move to the really clinical side. What happens when the machine itself wears out or breaks down genetically?
Well, before we even get to genetics, we have to talk about ROS, reactive oxygen species.
The exhaust fumes from the engine.
That's a great way to put it. Lehninger points out that the chain isn't perfect. It's incredibly efficient, but not 100%. Sometimes an electron escapes. It leaks. This usually happens at complex high or complex 3, and if a single electron jumps directly onto an oxygen molecule, you get superoxide, O2 with a negative charge.
A free radical.
A nasty one. It's a chemical vandal. It will attack lipids, proteins, and most importantly, mitochondrial DNA.
We do have defenses against this though, right?
We do. We have enzymes like superoxide dismutase and glutathione peroxidase. They are the cleanup crew. They mop up the spills, but they can be overwhelmed.
And when are they most likely to be overwhelmed?
Paradoxically, often during hypoxia when you have low oxygen.
Right.
Or when the chain is stalled for other reasons. If the chain is just packed full of electrons that have nowhere to go, like when you have high NADH but no ADP, the likelihood of a leak increases dramatically.
This accumulation of damage over a lifetime, is this the theory of aging?
That is the mitochondrial theory of aging. The idea that our power plants slowly poison themselves with their own exhaust. Over decades, they damage their own DNA, which leads to worse function of the complexes, which leads to more leaks, which leads to more damage. It's a vicious cycle.
Which brings us to mitochondrial DNA. It's unique, right? Your mitochondria have their own separate genome.
They do. A tiny circular genome. It only codes for 13 proteins, but all of them are essential parts of the respiratory chain complexes. And here's the real kicker. It's maternally inherited. You get all of your mitochondria from your mother, from the egg,
Thanks, Mom.
and if your mother has a mutation in her mitochondrial DNA, she passes to all of her children. But it's not all or nothing like nuclear DNA. It's a concept called heteroclasmy.
What's that?
Well, a single cell has hundreds, maybe thousands of mitochondria. Some might have the healthy DNA, some might have the mutant DNA. The severity of the disease depends on the ratio of good to bad. And it's a roll of the dice in every single tissue division.
Harper lists a few of these diseases, and they have these intense acronyms. Let's look at MELAS.
MELAS. That stands for mitochondrial encephalopathy, lactic acidosis, and stroke-like episodes.
That's a mouthful. Break that down for us.
It means the brain runs out of energy. The patient has what look like strokes, but not because of a blood clot. It's because entire regions of neurons simply fail. They have a brownout. And the lactic acidosis happens because all the cells are trying to switch to anaerobic glycolysis to survive, and they're just pumping out lactate. It's often a defect in the genes for complex I or complex Phi.
What about MRF?
MRF, myoclonic epilepsy with ragged red fibers.
Ragged red fibers. That sounds like a heavy metal band.
It does. But it's actually a description of the muscle biopsy. You take a sample of muscle from one of these patients and look under a microscope. You see these huge clumps of diseased mitochondria accumulating under the muscle cell membrane. They turn bright red with a specific stain. It's the muscle cell desperately trying to make more mitochondria to compensate for the broken ones, but the new ones it makes are broken too.
And the last one here, LHON, Leber hereditary optic neuropathy.
This one is just tragic. It's often a sudden onset of blindness in young adults, usually men. The optic nerve is one of those energy-hungry tissues in the body. If complex I is defective, the optic nerve just can't maintain its membrane potential. It dies.
There's a very clear pattern here. Brain, muscle, eye, heart.
Exactly. Mitochondrial diseases hit the tissues with the highest energy demand first and hardest. If your city's power plant is failing, the first things to brown out are the factories and the skyscrapers, not the little LED nightlight in your hallway.
It really highlights how completely dependent we are on this constant invisible flow. We just take it for granted.
It does. We aren't static statues. We are flames. We are systems of constant energy flow. And this pathway is the wick of that flame.
So let's wrap this all up. We've covered this incredible journey, from food to NADH, from NADH to the electron transport chain, from the chain to the proton gradient, from the gradient to the spinning turbine, and from the turbine to ATP.
It's a system of controlled release. It takes the chaos of chemical combustion and channels it into a disciplined rotary current.
Discipline, that seems to be the word of the day.
It really is. The tight coupling of oxidation and phosphorylation is biological discipline. We burn exactly what we need when we need it. When we lose that discipline, through uncoupling, through poisons, through genetic leaks, we get waste heat, damage, and death.
It's humbling.
It should be.
I want to leave our listeners with a final thought to chew on. We talked about how mitochondria have their own DNA. We talked about how they look and act a lot like bacteria.
Because they were bacteria.
Right. The endosymbiotic theory. 1.5 billion years ago, a bigger cell swallowed a bacterium and, for whatever reason, didn't digest it. They made a deal. You give me energy, I give you shelter and food.
A deal that fundamentally changed the course of life on Earth. It allowed for the evolution of all complex life. It allowed for us.
But think about what that really means. That bacterium never truly left. It's still in there. We are powered by what are essentially alien engines. Ancient bacteria living inside us, retaining their own strange little genomes, and when they get sick, we get sick. So are we just the vessel? Are we just the tank driving the real engine around?
That is a thought that will keep you up at night. Are we the host, or are we the exoskeleton for our mitochondria?
On that note, go thank your mitochondria, take a deep breath, use that oxygen, and appreciate the voltage drop.
Keep the gradient strong.